Okay, so welcome also from me and Marty, who's sitting there in the back. So you can probably guess who's Marty and who's me. So who's not been to any of these before? Who's not been to any of these before? All right. So better introduce ourselves a little bit. So that's Marty Rost. That's me, Burkhard Polster, and we're the Maths Masters, believe it or not. We actually didn't give ourselves that name. I don't think we would have given ourselves the name. That was somebody else's idea. And that was a couple of years ago. Simon was approached by The Age. They were looking for some people to write some maths articles for them. And we had been doing things for Simon for a long time, these kind of public lectures. At the time it was at the Melbourne Museum. So he arranged a meeting with the editor, the education editor, Ken Merrigan, and we started writing columns for The Age. And they gave us this name, so they gave us the name. We were the Maths Masters. We were the Age's Maths Masters, and so we're now the Maths Masters. All right, so just a little bit about ourselves again, just like last time when I talked about the Cube. It's our webpage, there's lots and lots of things there. Today I'm going to talk about an aspect of what we're doing. It's actually pretty much the main thing we're doing, is writing articles pretty much every week. So up there is a link to the latest article, and there's an archive here. It's the Maths Masters archive. And here you've got just the list for this year, that's 2013 and 2012. It's actually about 215 articles now. So 215 articles, and so far no end in sight. Even this year, no end in sight. Bit of a break. I mean, we always take a break during school holidays. But anyway, so today what I promised to do was actually look at those 215 articles and pick like a couple that I like particularly and talk about them. And I had a look at all 250, and I loved them all. So that was a bit of a problem. So what I decided to do is I'm going to go all the way back. So let's go all the way back. So 2012, 11, 10, 9, and that's where it all started here. So what I'm going to do today is I'm actually going to start at the beginning and just work my way back and see how far I get. And then let you go and read the rest. It also makes a little bit of sense to do this sort of thing because at the time, at the moment, the articles appear on the web. So there's a little bit of a blur usually in the printed newspaper, which is something like a pointer to what's going on the web. But all the articles appear on the web. But actually in 2007 and 2008, everything was in the printed part of the newspaper until they had their cuts and they pretty much cut out the education part of The Age. Anyway, we survived on the web, but we had serious limitations to what we could actually say at that point in time. There was like 300, 400 words that we could do, and maybe one picture. And these days we're probably like 1,200 words and 500 pictures. So it's all changed. And one regret was always there was almost so much more to say about these topics that we were writing about. And so I thought, well, might as well do it today. Right? We'll start with the first one, pattern power. Power. Have a look at these numbers and you tell me what's next, okay? So 2, 4, 8, 16, what's next? 32? Who thinks it's 32? 32? Yeah? Yeah? Well, I beg to disagree. I think it's really 30. I'm going to prove it to you. Yeah, I'm going to prove it to you. So what I'm going to do is I'm going to make up a pattern. Okay? So here's a really nice pattern. So you've got a circle, and you put some dots on the perimeter. So there's 1, 2, there's 3, there's 4, there's 5, there's 6. And then we draw all the possible connections between those dots. And those possible connections, they chop up the circle into a number of regions. Now we're going to count them, okay? So really nice pattern here. So there's 1, 2, there's 1, 2, 3, 4, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now it gets a bit big, so you have to all help me count now. So who's going to help me count? Ready to count? Okay, here we go. So it's 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So it's really 30, it's not 32. Well, I mean, I've talked about you know, mathematics last time. Right? So in mathematics, if you do mathematics, like everybody in school does mathematics, if you give as an answer 30, it will be wrong. The only possible answer to 2, 4, 8, 16 is 32. And so in all IQ tests or any test that you might ever encounter, the only possible answer here is 32. But actually it's not. This is a really nice pattern that shows it's 30. And in fact, there's another one. So here we've done is we've put the points like nicely spaced around the circle, but actually if you just put them kind of randomly, then something happens in the last picture here. So for these pictures, so randomly distributed, you still get 2 areas here, 4 here, 8 here, 16 here. But here you see this triple point in the middle doesn't happen in a picture like that. So the triple point actually opens up into an extra little triangle in the middle. And I need something else here. Okay, so you see that there's this little triangle here in the middle that's extra. So you can actually get 30, 31. So for arbitrary distribution of points, you actually get 31. So 31 is also a good answer to what comes next. In fact, there's a really amazing resource on the web that I recommend to everybody, and it's called the Online Encyclopedia of Integer Sequences. And so what it does is it's collected lots and lots of sequences that appear naturally in mathematics or in nature or wherever. And so whenever you come about a sequence that you think, well, what comes next? What you can do is you can just type it in here. So for example, I've typed in 1, 2, 4, 8, 16, and you press search, and it will look up all possible naturally occurring sequences that start like this. So I have 1, 2, 4, 8, and 16 in it. And so if I hit this, it finds 567 different sequences. And the first one is really the powers of 2, but there's other ones. So there was our 31, right, the one I showed you. Here's one number of positive divisors of factorial, so that gives 30. It's a completely different 30 from the one that I just showed you. Right? So if you look at what that means is, if you look at 4 factorial, for example, 4 factorial is 1 times 2 times 3 times 4, and you look at all the number of positive divisors, you get, it's 1, 2, 3, 4, it should be 4. Yeah. Okay, then another one, here we've got 23 as the next one here. That's a really weird one. So we've got 1, 1, 2, 4, 8, 16. So how does that come about? What you do is you start with 1, then you say, well, there's only 1 digit so far, so we'll do 1. Then you count 1 plus 1 is 2. Then we do 2 plus 1 plus 1 is 4. Then we do 4 plus 2 plus 1 plus 1 is 8. Then we do 8 plus 4 plus 2 plus 1 plus 1 is 16. But now it gets weird because we do 6 plus 1 plus 8 plus 4 plus 2 plus 1 plus 1 is 23. And now we do 3 plus 2 plus 6 plus 1 plus and so on. And it gets just completely weird. Other sequence, still pretty natural, right? So natural. Okay, so 23 is also a good answer. And here's something about payphones, and that gives you 36. And there's 500 something other ones, right? And in fact, in our article, we say we can make any number the next number. We can actually write down a formula that spits out on input of 1, 2, 3, 4, 5, 2, 4, 8, 16, and then whatever you want. So for example, we claim we can make up a formula which spits out pi. Yeah, we can. And here it is. Great. So that's the formula. And if you put in 1, it spits out 2. If you put in 2, it spits out 4, 8, 16, and then as the fifth number, if you put n equals 5, it actually has as output pi. So you can do anything. Now, this was actually the whole article here. The whole article. Our first article, we're very proud of this article. Except there was something not quite right about this article. Can anybody see what's not quite right about this article? What's not right? It's kind of really staring at you. Now have a look at the diagrams. Have a look at the diagram. Ah, yes. So the line was missing. So obviously the way you communicate with the agents, you write this up and then you give it to them, and then they give it to a graphic artist, and then the graphic artist forgets the line, which kind of messes up everything. And I mean, this has been kind of an ongoing battle, right? So 215 articles, and the first 2 years we had like lots of these things happening, and it was very, very good to open the Age on Monday morning and see what did they do to us actually. Okay, so there it is. So now actually we've got an archive for these things, and I've just put the line back in. So nobody knows that it ever happened, apart from you guys. Okay, and you know, obviously that was a short article, so already now what I've told you, most of it's not in there. Right? But I'll tell you a little bit more. I'll tell you a little bit more about this sequence of numbers there, where it comes from. Has anybody seen this triangle here? It's actually quite famous. So what's the triangle?
Pascal's triangle.
Pascal's triangle. Okay, so if I point at a number, this one here, how do you get this number from other numbers in here?
Add the 2 ones above it.
Yeah, that's right. So you just go to 2 ones above, and 4 plus 6 adds up to 10. If you go anywhere else, like 21, 15 plus 6 is 21. You know, 35, 15 plus 20. So it's a nice, there's a nice pattern here, but it's also a very important object within mathematics. Comes up in all kinds of contexts. You know, it's basically one of the superheroes within mathematics. This kind of triangle. It's called Pascal's triangle. It's got lots of nice other objects associated with it. One of them is, for example, if you add up the rows here, so if I add up this 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1 plus 3 plus 3 plus 1 is 8, so you get the powers of 2 here. Right? So the rows add up to the powers of 2. That's one thing which is quite nice about it. Now, if you actually want those numbers here, what you do is you take the first 5 of those numbers. Let's have a look. So, for example, for one, let's see, we take, so the 31, for example, is 1 plus 5 plus 10 plus 10 plus 5. That's the first 5 of these guys. For the next one, if you did a 7 gone, you would have to do 1 plus 6 plus 15 plus 20 plus 50. Right? So it's 7 minus that one is 57. Right? So it's 57. This would be the next one. And then here, if you add up those guys, it's 99. So the next one would be 99. So that's kind of a nice thing. It's also can be turned into a formula for actually these numbers. It's a very nice formula for these numbers. I'm not going to tell you why this is the case, but you know, it's okay. Then these guys here, well, this is kind of something completely screwed up, and it gives rise to this nice formula here. Now this is something completely nice in terms of pattern, right? You've got equally distributed, equally spaced points around the perimeter. But actually the formula is very crazy. I mean, it's actually a lot harder to get the formula. It's actually only, like this sort of pattern you've probably seen, or people have been looking at those patterns for a long, long, long time, but it was actually just fairly recently that somebody figured out a formula for this. Actually figured out lots of things about this. In fact, I just want to ask you, I mean, can you imagine just going forward maybe to 30 points around the perimeter? What something like this would look like? Can you imagine what something like this would look like if I started with 30 points? Or with 100 points? Can you imagine what that looks like? Okay, I'll just show you what the screwed up one looks like. So it looks like this. It looks like a mess, right? It looks like a real mess. And here I've got the numbers here. So that's one of them. There's another number up there. What's that number, we think? What's that number up there? That's the number of different areas, that's right. But what's the number up there? That's actually 2 to the power of 30. Right? So if you go on like 1, 2, 4, 8, 16, 32, 64, and so on, and you go up to 30th, then you get that one there. But at this stage, the difference between the number of regions and that number is pretty amazing. Now, can anybody imagine what this one here would look like? 30. it's pretty hard to see. Pretty hard to see. I'll just show you. So that's 30. So that's 30 points, completely nice and regular. And there's lots of other things starting to happen in here, right? So you can see all sorts of kind of circles happening. So there's kind of circles in here. Lots of circles. There's these points in which things intersect like crazy. There's like little eyes opening up here. Just to describe what's going on here, just these features that you only discover when you actually take this to some sort of extreme. It's actually quite tricky. And as I said, it's only been done like in 1998. So let's have a little bit of a look here, closer. So one of the things, actually just backing up to, like when you look at these numbers here, numbers of regions, why was there one more region here? Why was there one more region? Does anybody remember what it says? Yeah, it's irregular. And so what's not here in this picture that's here in this picture? The middle, right? So there's in these sorts of pictures, what can happen is that there's several lines going through a point. With these messed up pictures, when you see a point of intersection in here, it's always two lines intersecting there, never more. In those, other things can happen. Let's just go to 4, and I've got like a zoom into some of these points. So see here, there's 2 lines intersecting, there's 3 lines intersecting, there's 7 lines intersecting. So there's 1, 2, 3, 4, 5, I think. 5 lines intersecting. What do you think is the maximum number of lines intersecting in something like this? So if I say I take like 1 million, so 1 million points on a circle, and I let it go, right? And I see all these kind of intersections inside. How many lines maximum do you think can be there? Can it be? In the middle, that's right. In the middle, there's going to be lots of them, actually lots of them. But if you go away from the middle, what's the maximum? Right. So if you've got like a million, then there's opposite this guy here is somebody, opposite this guy somewhere, and all these are going to intersect. So it's actually going to be 500,000 meeting in the middle, right? But if you go off the middle, there's also going to be points at which things are going to intersect. And so how many do you think maximum can there be? So that's something that was actually quite hard to figure out. And the maximum was actually 7. So it can never be more than this. So it doesn't matter how many points you do, it can never be more than 7 lines to a point. And kind of getting this under control is exactly what you need to be able to figure out how many regions there are, and how many intersections there are, and all kinds of other things. And somebody did that, and eventually, that's the formula. That's the formula that you need to figure out how many regions there are. This thing is actually called the magic rose, and it's called the magic rose because it reminds people of these church windows, which are also called magic roses. Anyway, so there was about 20 times the amount of stuff that was in the articles, but I just thought I had to do it at some stage, so I did it now. All right. Okay, so this is the second article. The second article was about Federation Square. Now, I'm actually not going to go talk about Federation Square because I've just done it last year, and we're going to do it again pretty soon. Simon's already said so. There's going to be 3 more talks. It's going to be the Festival of Mathematics. It's going to be at Fed Square, and it's going to be not only for general audience, but also for people who teach mathematics at school to just bring in their kids, and in a big lecture theater, like 300, 400 people, and we're going to tell them about all the maths that can be found in Federation Square and all around Melbourne. Okay, so I promised you to talk a little bit about the first couple of articles. So, well, we're going to talk about some kind of architecture. We've actually talked lots about architecture, and all of these things have been covered. So there's Eureka Building, there's something on Swanston Street, RMIT Building, there's the facade Federation Square. That's in front of Chadston here. That's actually, these 2 are new, so we've only discovered them this year. So does anyone know where this one is? Any regulars? Healesville Sanctuary, that's right. So there's kind of a medical center at Healesville Sanctuary. The roof is highly mathematical. It's a minimal surface, so something that people get very excited about. Like Marty's PhD is about minimal surfaces, so he was very happy when he found this one. And this is the Kleinbottom house on the Mornington Peninsula, which is also something nice. But one of my absolute favorites is this one here. Does anybody know where this one is? That's the big pineapple. That's the big pineapple, and there's in Queensland somewhere. I've actually not been there, still, do a pilgrimage there. Although in the article it said, there was the first article in 2011, and we actually start by saying, we've just been to the pineapple. Sometimes we lie, right? when it makes for a nice story, we lie. And we actually still have to go there. Right? I mean, I had some email correspondence with these people, but I've actually not been there. Okay, so we talked about pineapples. Does anybody know what's kind of special about pineapples? Some people probably read about. Does anybody know what's special about pineapples? What's supposed to be special about pineapples? No? Okay, I'll tell you. So if you take a pineapple, you go to the supermarket, take out a pineapple. Like in the pineapple, you see kind of spirals. So there's spirals kind of going around this way, and there's a spiral kind of going this way, and then there's an even steeper spiral going that way. And actually right next to that spiral here, there's another spiral that goes in exactly the same way. This one here, and you can actually count the number of spirals going around like this. So there's a number of red spirals, there's a number of blue spirals, and there's a number of green spirals. And the numbers are very impressive. The numbers are 5, 8, and 13. Does anybody recognize these numbers? Fibonacci series, that's right. So you all remember that. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21. And sometimes you actually do get pineapples with 8, 13, and 21 spirals. And when you look at this sort of stuff up on the left, it says it's always like this. It's always like this. You're always going to get 5, 8, and 13, or 8, 13, and 21. There's no exceptions. And, well, Martin and I were the maths masters, but we're also the mathematical mythbusters. So if you have a look at our 2015 articles, there's a lot of myth busting going on. And one of the myths we wanted to bust is, well, actually, if you go to the supermarket and do this, and I've done it, and Marty has done it, you actually find that these numbers are not always 5, 8, and 13, or 8, 13, and 21. There might be something to do with gene manipulation, but I don't believe it. If you go to Australian supermarkets, you'll find like perfectly grown pineapples, not screwed up ones. Maybe at the molecular level, but I can't tell. That don't follow this pattern. But there's actually a different pattern. Which is not quite as strong as this Fibonacci stuff. That is there. And I just want to show you how that works. It's actually something that we kind of discovered on the way up. I'm sure somebody else has seen it before, but I've never seen it kind of, I've never really seen it in print. But so always they say it's Fibonacci numbers, or something else. There's actually a really nice explanation for something. If you look at the numbers in the big pineapple, for example, that's 13, 13, and 26. So that's definitely not Fibonacci, right? But actually, when you look at 5, 8, and 13, and 13, 13, 26, they have something in common. And the thing that they have in common is what I want to tell you about. So that's the rule, there's a rule. So what do you think these two triplets have in common? What do you think they have in common? Yeah?
The green one plus the blue one is the red one?
That's exactly right. So if you take the two smaller ones and you add them up, you get the bigger one. And of course that's exactly what happens with Fibonacci numbers. Two smaller ones add up to the bigger one, so that's fine. But we've got something happening here which is a little bit less strong than Fibonacci numbers, but still it seems to be, I mean, at least the pineapples that I looked at, they follow this rule. So there might be different numbers, but the two little ones, they add up to the bigger one. That rule seems to work. And I just want to show you how you can actually convince yourself of this. You can make your own virtual pineapples. You just get some hexagon paper, you download it from the web, and then you kind of roll it up like this. Okay. So like this. And then you get basically a virtual pineapple. Huh? You can also make up these sorts of things, where it's kind of taking a piece of paper, kind of wrapping it around a pineapple, and then tracing out hexagons, taking the powder like this to get this, right? So basically all nicely grown pineapples correspond to something like this. So we can go the other way and construct pineapples by rolling it up like this. But not only this way, what you can also do is you can make things kind of go screwy, so kind of spirally, really spirally, by shifting things along like this. Or shifting things along even more, or maybe rolling it in a bit more. And you can all get your own hexagon paper later on when you're going to walk out of here. You can try this at home. So I just do it like this. And I just staple things together like that. And maybe a bit more. But we lose these things. Okay, and now once you've got something like this, and there's lots and lots of different choices, okay? Lots and lots of different choices. We can actually make these, we can make real pineapples, patterns, we can make lots of other ones. You can start counting spirals. I'm just going to do it for you with this one here. So there's a spiral here, okay? And then we do another one here, so it's 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10. Okay? We must note down 10. And we get another pen. And we go like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's a 14 here. And now we need one more color and one more kind of spiral, and that other spiral is kind of quite shallow now. This goes like this. So I'll just have to highlight it a bit more, so that actually repeats itself, right? So it repeats itself. So then we get 1 spiral, 2, 3, 4. So it's 4. And 4 plus 10 is equal to 4 plus 10 is equal to 14. And you can actually show this mathematically. It's actually not very hard to prove that this is going to work. So this is a rule that actually works and that actually explains something. I mean, you can explain this business of the two small numbers adding up to the larger numbers quite easily. Now, if you actually want Fibonacci numbers, which don't happen actually, it's going to be hard, right? But people explain it anyway. So something to remember here, and something you can only learn from the maths masters, it seems, because I've never seen it anywhere else. Okay, and this is actually one of the kind of the pleasures of writing these articles. You kind of pick a topic that seems interesting, and then you have a really, really close look. And one of our aims is always to find something. We might be writing about something like this that millions of people have been writing about, but what we always try is to find something new to say. And this article, for example, we really had something new to say, this tiny little insight there. And if you want me to give a proof, it can also come out later and I'll show you. All right, now, this was actually one that Marty, I think it is. I mean, if you actually follow these things, one nice thing to try is to predict who wrote the first draft for an article, either Marty or me. Right? So, I mean, you have a look at some of these articles, you listen to some of our talks, and then you try to pick. This was Marty started this one, or Robert started this one, and So, I mean, usually if it's something about trashing calculators, for example, with a hammer, then that usually has something to do with Marty. I mean, I also do this occasionally, but usually it's more accidental. For example, I just broke the screen of my laptop here, but I actually didn't use a hammer for this. Now, if this was Marty's laptop, then you could count that there was a hammer somewhere in the desk. All right. Anyway, so this is another nice article. It was basically the third article. That was the third article that I wrote about, and it's about something that happens quite often. You kind of take a table and put it out in the backyard, and you want to have a barbecue. But the first problem you have to overcome is that the table actually wobbles. Right? So on uneven ground, this thing won't stand. Still, it will just wobble, so it's a bad thing. We have to somehow fix this. And, well, we wrote about this sort of problem previously for the MIV. So there was, they have a little magazine for secondary school called Winkelung, and we had the back page of that for ages, and we wrote about this, and had a nice mathematical solution, but somebody questioned us, and then we had a really, really close look, and then kind of spent half a year not doing anything else. But in the end, it was not in vain because we got to write math master article too. Anyway, so I'll just show you something nice mathematical about this. So here's something nice. So this is the equator here. This is the equator, and these are two antipodal points. When is a point antipodal? When are 2 points antipodal? Well, antipodal, right? So there's like this north pole and the south pole here, and the other one on the other side, they're antipodal. So they're opposite ends of the Earth. So this antipodal points, these ones are antipodal points. And like there's a mathematical theorem which says that at any point in time, there are two antipodal points on the equator which have exactly the same temperature. So right now there's 2 points on the equator that have exactly the same temperature. Exactly the same. And there's no way of predicting where those 2 points are. But we still know there's 2 points, at least 2 points. There could be more than 2 points, there's at least 2 points there, we don't know. But I can show you that there's 2, okay? So I'm going to show you how there's 2 points on the equator. So here we've got 2 points on the equator, let's pick any 2. Measure the temperature. At the moment, there's 10 degrees here and 20 degrees there. Okay? All right. Now, what I'm going to do is I'm going to put you at this point, and I'm going to be at that point. Okay? Now we're going to start running at the same time. But actually, we have to do one thing. We basically have to freeze action in terms of what the Earth does, in terms of temperature changes. So Earth is just kind of standing still while we're doing this, right? But we're not standing still, we're running, okay? So you're running this way, I'm running that way, okay? And we always make sure that we're exactly at opposite points of the Earth, okay? Okay. And we do this basically 180 degrees. So let's just do it 180 degrees. So almost around, and then we're, swap places, okay? We swap places. So what's the temperature now at, well, who are you? Oh, you were this one here. Who were this one here? So you measure temperature now. What's the temperature? Where you are? 20, right? And I'm measuring temperature. It's 10, right? Because we've got to swap places, okay? So it's like that now, okay? Okay. Now the other thing you did while you were running out of the Earth is you measured the temperature at every single instant. You put a little thermometer and measured, and then you graphed it, okay? And then you graphed it, and you found this. Okay? So that's what you came across in terms of temperature. Okay, I do the same sort of thing. Okay, I do the same sort of thing. So I also draw something. And so what can you tell me? Maybe it's a bit hard to predict what that would be, although you can kind of figure it out. But I have to get from here to there, right? I do it somehow. I'm graphing. What's going to happen here? There's something in between, right? So they definitely go to cross somewhere. Are they going to cross? Yeah, I don't have a choice. Right? I want to draw my temperature distribution here. I can try something fancy here, but whatever I try, I'm definitely going to cross here somewhere. Right? So somewhere, I don't know where, but I'm going to cross. So what does it mean for these two curves to cross? That means that the temperature here is the same, right? The temperature is the same. It's just that. So at this point of kind of going around the Earth, the temperature is exactly the same, right? And I mean, usually we can't do this, right? We can't freeze action, we can't run around, we can't measure temperature. None of this is possible. But I mean, this picture that we would get if we were able to do it would be exactly that. There would be a point at which temperature is the same. So these things exist, but we have no idea how to actually pinpoint them. And that's something fairly powerful that you can only do in mathematics. All right. Now here's the real problem. Okay? Wait. It's true. And magic.
The problem with some breakfasts is, well, they're unbalanced. They're either just tasty or just good for you. But if you're into balance, you'll love new Just Right berry and apple flavour. With apples, strawberry pieces and the goodness of whole grains, it's a perfect balance of the fruit you love and the goodness your body needs. New Just Right berry and apple flavour.
All right. So it's a problem that many people are facing. All right. So I'll just make up a kind of a mountain top here. All right. And I want to show you that, that there's a nice trick that pretty much always works, and that is if you've got a table and it's square, okay, square table. It also works for rectangular ones, but I'll just show you for square. Then you put it down in your backyard, say like sort of like that, okay. So now, and you see the two, so we've got two red ends here, the two red ends. They touch the ground, but the table wobbles like this, okay? The table wobbles like this, and goes back and forth. So what I can do is, I can turn the table on the spot. And then if I just turn long enough, I'll actually find a position where all four legs touch the ground. So at the moment, all four legs touch the ground. And that pretty much always works. Now the only thing that needs to be the case for this is that these endpoints here, they form a square or a rectangle. Will have to form a square. And then you don't have to worry about sawing off legs or anything. You don't have to wedge anything under. You can actually just, you just put it down anywhere in your backyard and you just turn the table and there will be a point at which all four legs touch the ground. It's pure magic, right? And it's maths. So you can actually show that there's going to be a point like this, just the same way like we did with the equator. And I'm going to do it in a second. All right. So remember this for next time. It not only works for tables, like but I use it mostly for ladders, right? So ladder, you kind of bring it out like this, then you've got a rectangle at the bottom, you put it anywhere it wobbles, you just kind of turn it around a bit, and all four legs are going to touch the ground. So without any other interference necessary. Okay, now, so this is kind of the setup that I want to do. I want to again have two of these legs touch the ground, and the others are kind of in the air. So at the moment, I've got red touching, and the yellow ones I can adjust. I can just wobble it so that this yellow one is the same distance above the ground as that yellow one. Okay, that's how I'm going to start. Right? So these two touching, and these two same distance above the ground. So that's how it is. So there's the table. Right? Okay, so two touching the ground. This one here and that one here. And I've adjusted the other two so that this distance here is exactly the same distance as the other one, right? You can wobble across these here. Just go back and forth. Okay. Alright, at the moment the yellow ones or orange ones are 5 centimeters above, and these guys are smack on the ground. Okay? And now I'm going to start turning. Okay, so I've got my two guys here, and I'm going to start turning. So I just want to do like 90 degrees. I only have to do 90 degrees until the yellow ones swap places with the red ones. That's what I'm going to do. Just 90 degrees, and you find one of those points. Guaranteed. Okay. At the moment, these two guys are touching. These ones are 5 centimeters above. What I'll do is, during this rotation is, I'll always make sure that these guys here are touching the ground. They always touch the ground. And I always make sure that these two guys are the same distance from the ground. Right? So 90 degrees, so slow rotate. And I make sure that these are always sliding across the ground. And I also always wobble the table in a position so that these two guys are the same distance from the ground. Okay? Everybody got that? Okay, so let's just do this. So 90 degrees, we rotate, and then of course these guys are always at 0. Okay, so these guys are always at 0. Now, the the orange ones have changed places with the other ones. Okay, so what's different now? What's different now? What's the distance of the orange ones from the ground at this point in time? Right, so we've got these two guys facing this way. Now they're facing that way, right? So they've taken kind of the place of the orange ones, but now the whole upper thing is kind of just 5 centimeters down, right? So what's the distance of an orange one now from the ground? What's it? What do you think? It's -5. It's exactly right. It's -5. To get from here to there in one step, you just take the whole thing and bring it down, because then these guys start touching. These kind of sink into the ground, and so what actually happened during our 90-degree movement, if you just do it right, is that some sink into the ground. Okay? And now you can actually, just measure the height above the ground of the yellow points or the orange points. And what's going to happen if you go from here to there? What's going to happen? At some point in time, it's going to cross. So everybody is at 0. That means at some point in time, you're going to have all 4 legs touching the ground. So it's pretty manageable. All maths. Okay. So who's going to try this? Well, more than that, please. You're all going to try this. Next time anything wobbles, you try it. Okay? Okay, so the main thing, I say it again, is that what you've got here at the ends is a square or a rectangle. Okay, so let's just have a look at what's wrong with our article that appeared in the Age. What's wrong with it? What's wrong with our article again? The graphic artist got hold of an idea and did something with it. One leg is shorter. Okay, so I mean, the wobbling can happen also because the leg of the table is shorter, right? So let's just say it's shorter now, right? It's also wobbling. Can you fix the wobble by turning the table now? You can turn as long as you want. It's always going to hang in the air, right? So that's not going to work, right? So just in case it doesn't work for you, don't blame us, blame the table, okay? But actually, I mean, even if it's slightly short, I mean, usually you will find that point. It's a bit hard to quantify, what works and what doesn't work. If it's precise and if it's just the ground is just wobbling a little bit, it's going to work. But if one of the legs is actually too short, well, it's sometimes it works and sometimes it doesn't, but still worth a try. Okay. So that's actually what it's supposed to be like. All legs the same, and the ground's correct. And we actually got an article out of this, together with some other people, and we even got onto TV. Well, not we, but Marty. So prepare for a shock. When Marty comes on, you all have to give me your best reaction. Okay?
Now, if you're about to sit down to lunch, then this story could make life a little easier for you. An international team of mathematicians has explained how a wobbly table can be stabilized without needing to jam a coaster or a napkin underneath the offending leg. It's all down to intermediate value theorem, or in other words, if you keep turning a rectangular table on most surfaces, the wobble will disappear. Dr. Marty Ross is one of the mathematicians who joins me now from Melbourne. So, Dr. Marty Ross, how does this work? Can you just explain?
Well, we'll save ourselves the explanation because I've just done it, right? But again, if you want to see the rest, it's actually on our website. We've got it on the website, right? Yeah.
Not after the lecture.
Anyway, it's a really good thing. So, I mean, this sort of stuff happens pretty often, actually. Okay, then we had tax time coming up, and we talked about how to cheat on a tax return, so very, very applicable. And then we had something about Sudokus, which was mainly motivated by a friend of ours being Sudoku king at Monash. And then we had something about, right, so who do you think wrote that up? Well, I still think footballs are spherical. No? So I still don't quite believe that they can have any other shape, and they shouldn't have any other shape. but Marty tells me that somewhere here in Victoria people actually play a game that's played with a ball that's not a sphere. Anyway, so I learned something, I learned something. Now, most of these, I'm not sure what it is. Maybe we'll skip this one. Let's just go forward a little bit. Just a couple of other ones. Oh, right. So one thing you notice in many of our articles is these strange objects that start appearing. So, for example, this one here, this object. It's about this curve that you get when you sit in a coffee shop and the sun's shining and you get this distinctive thing. So we talked about this one in one of those early articles. But what's really important, but didn't tell you about, is that this is my coffee cup. And lots of these like strange objects or people actually have to do with us. So there's like one person sitting right there, and there's another person sitting there. There's a cat there, there's our cat, and then there's Marty's little one, and so they've all featured in these articles. So it's a matter of finding them. Okay, then I just went to 2010, 2007. That's the other articles here. No, definitely don't look at this one. It was full of mistakes. Okay, so I think last thing I'll do is actually talk about something that a lot of people ask us about. So in this picture, this is called. I've taken this from an old TV series called The Time Tunnel, because I was kind of going back in time with it today. They ask us about this picture here. What's the pizza about? Okay? So I'll just tell you about the pizza, okay? Just in case you were wondering. So you go to a pizza shop, and there's 3 different sizes of pizza. There's the small pizzas, medium pizzas, and large pizzas. Now, they have a special offer. The offer is that the small and the medium together cost exactly as much as the large one. Okay? Small and medium together cost exactly as much as the large one. The question is, how can you decide really quick which of those 2 combos to go for? Right? So in terms of price, they don't differ. So what you want to maximize is obviously the area. Right? So you want to maximize is the area of this plus that greater than that, or the other way around. So what's a really, really quick way of deciding this? What's a really quick way of deciding? Some people kind of know. Well, I'll first show you with a mathematical pizza shop. In a mathematical pizza shop, you have 3 different square pizzas. So how do you do with three square pizzas? 3 square pizzas. Basically, what I do is I give you the trays. I give you 3 trays, right? 3 pizza trays, and I want to decide, like within 3 seconds, which combo to go for. Does anybody have an idea of what we do with the 3 pizza trays and decide in a what do you do? 3 squares. Anybody? Pythagoras. Okay. So let's just say we put the trays together like this. What does that mean? If you like put 3 trays together like this, what do you choose? What do you choose? It doesn't matter. Why? Because this square, so a squared plus b squared equals c squared, right? So the 2 small pizza trays are just as big as the big one. So it doesn't matter. So you can choose this one if you like it better, or you can choose that one. What about here? Which one do you go for? Which one do you go for? You go for the big one, right? So basically, these 2, they are really the same here in this picture. So what happens is I just move them apart a bit more. And as I move them apart, this square goes up. So we go for this one. Okay. What about that one here? What should you choose? Small one. That's right. Okay, so choose the 2 small ones. Okay. Now back to the real question. And here's the hint what you should do. The hint is a chainsaw. So I give you the pizza trays plus a chainsaw, okay? And then you decide real quick what to do. Okay, so somebody wants to give me an idea of what to do? Eat the pizza? No. Because you have to decide. Okay, what do you do?
Cut the pizza tray into quarters.
Oh yeah, that would be a good idea, yeah. And what would I do?
And then use so that you take 1 square of each pizza tray.
Okay, yeah.
And arrange it in that triangle.
That would be good, but actually you don't have, it's perfectly alright, you can do it with quarters, but you can also do it with just halves. So what we're going to do is we're going to just cut these things in halves, and we've got an explanation here with Marty and me, and it's probably going to be the last thing that we're going to do. So we're actually famous. And we are on TV, you know. So this is
Hi, I'm Burkhard.
I'm Martin.
We're mathematicians,
Quite hungry mathematician.
and we'd like you to join us for lunch.
First on the menu is pizza, but it comes with a problem to solve. Burkhard is giving me the choice of taking for myself either one large pizza or a medium plus a small one. And I want to choose the option which will give me the most pizza, but I don't know which one that is. Until I've done some fast maths to work it out. I cut each pizza in half and arrange the halves so they're sized like a triangle. Then I look at the size of the angle between the triangle's small sides. If its angle is greater than a right angle, which is 90 degrees, then the large pizza is bigger than the other two combined. But it turns out that the angle is slightly smaller than a right angle, which means that the small pizza and the medium pizza is my best bet. I'll take these two, Burkhard.
okay, and yeah, that was my strange tales from the Math Masters class. I think very much for coming today.
The Mathematical Association would like to acknowledge Marty Burkhardt's 2013 series at the Royal Society of Victoria. We thank the Royal Society for their support. But please do thank both Marty Ross and Burkhard Polster for a wonderful series.